Alright guys, welcome to Math 0314, section 6.1, square roots. Alright, so first thing we have to answer the question, of course, is what is a square root? So the square root, say the square root of 25, what it then is asking is what number times itself would give me 25? So 5 times 5 is 25, so the square root of 25 is simply 5. So this is what we mean by square roots. The square root of 49 would be 7, because 7 times 7 is 49. The square root of 0 would be 0, notice, because 0 times 0 is 0. And the interesting case is, what is the square root of negative 9? Now, some people would like to say it is negative 3. But negative 3 times negative 3 gives me a positive 9. So we have this problem because a positive times a positive is a positive, and a negative times a negative is a positive. So we have this problem of what is the square root of negative 9. And we, at some point in this course, we will come back and we'll talk about that. For right now, the only thing we can say is it's no real number. There's no real number that would actually solve that. So it's been a while, but real numbers are essentially all the numbers that we think about in the day-to-day lives. So like decimals, fractions, whole numbers, integers, negative numbers. These are real numbers, and so no value like that would work there. There is another point though of when we think about number 4, which is if a negative times a negative is a positive, then the answer to the first 3 is not just 5, 7, and 0. It's actually plus or minus 5, plus or minus 7. Now 0, if you say plus or minus 0, it doesn't matter. It's still going to become 0. So there are actually 2 solutions here, plus or minus 5 and plus or minus 7 to both the first 2. Now, there is a way of answering these questions called the principal root. And the principal root is essentially that when we have the option of saying positive or negative, we take the positive. Note, I said when we have the option of saying positive or negative. So what I had originally written here for number 1 when it was 5 and number 2 when I said it's 7, I wasn't solving for what are the roots. I was answering the question of what are the principal roots. So what are the principal roots of the square root of 36? 6, because 6 times 6 is 36. This is where we get into something that's a little interesting. So what is the square root of 4 over 9? Now, I'm going to do something that the text doesn't actually do, but I think is important to talk about right here, which is that the square root really means we're raising this to the 1/2 power. We're going to talk more about this in the next section, but you can't talk about square roots without mentioning that it really means raised to the 1/2. And the reason why we can't is that if we're raising 4/9 to an exponent, we know from the previous sections that raising to an exponent means that both the numerator and the denominator will have the exponent. So they both will have 1/2. What I'm really trying to say is that both the top and the bottom, you just take the square root of both, and this would come out to be 2 over 3. So whenever you see a fraction inside of a square root, you can just take the square root of the top, take the square root of the bottom, and write those results. Now what about number 7? Well, here we know that this means the square root of 4 over 100, right? If I jump 2 places, this becomes 100. So what I'm trying to tell you is that we're just going back to the same strategies we learned at the very beginning of this course, which is when you see a decimal, convert it to a fraction. So this means that this is going to become square root 4 over square root 100. Square root of 4 is 2. Square root of 100 is 10, and 2 over 5 reduces to 1 over 5. Now something else that's very interesting is that if I turned and I said, well, hey, you know what? I don't want to, in the beginning of this problem, play with 4 over 100. I actually want to reduce this to 2 over 25. Could I take, I'm sorry, I said 2 over 25. I meant to say 2 over 50, which then reduces to 1 over 25. So could I just have taken the square root of 1 over 25, which is the square root of 1 over the square root of 25, Well, sure, you would get the same answer. And the real nuts and bolts as to why is that these are in parentheses. So if you wanted to, you could play with parentheses first and then use the exponent rules to get to 1/5. So what I'm really saying is that as long as you follow PEMDAS, you'll be fine. Moving on to number 8. What is the square root of 144? Negative 144. So again, I want to stress, go back to number 4. We said the square root of negative 9 we can't do. So this one here, we can't do. I'm going to say that's the empty set under the reals. However, if the negative is on the outside, you take the square root of 144, which is 12, and then you just pop the negative on the outside. Okay. So what about number 10? Well, again, because the negative's on the inside, there's no solution. But when there's a negative on the outside, we can take the square root of the top, square root of the bottom, and just tack on the negative. So here I'm going to emphasize the fact that we said that this means that it's the square raised to the 1/2, which becomes 2. And something important to note here is that there is technically a little value here which is called the index. And when it's not written, the index is 2. Hence we have this 1/2. But the index is not always 2. So we see in 13 it is 3. So if the square root says what number times itself gives me 4, in this case 2 for number 12, then number 13 is saying what number times itself 3 times is going to give me 64. And that number is 4 because 4 times 4 is 16 and 16 times 4 is 64. So you have to be careful here because depending upon what the index is, this is what we're going to take the number to. So a lot of students, when they first see this, they make silly mistakes and say that this is pronounced the cube root of 64 is 8 because they know the square root of 64 is 8. This also brings up something that I've kind of been showing implicitly, but now I'm going to state explicitly, which is that you really need to know your squares. So you really need to know off the top of your head 2 squared is 4, 3 squared is 9, 4 squared is 16, etc., etc. Okay? You also want to know your cubes. So you need to know 2 cubed is 8, 3 cubed is 27, 4 cubed is 81. I'm sorry, 64. I just did that. And the reason why we need to know that, you really want to know this, is it takes a lot of time to sit there and go 2 times 2 is 4, 4 times 2 is 8. Especially as the numbers get bigger and bigger and bigger, it becomes harder and harder and harder. So my advice is to do exactly what I did when I was a student, which is don't actually memorize them, but as you come across them, write them down in a notebook and refer back to that notebook over and over again to reinforce what those values are. And before you know it, you'll end up having them memorized. Okay, the number 15. So this is the 5th root of negative 32. So a lot of people put this as the empty set because we said earlier you can't take the square root of a negative. However, this is inaccurate. This is not true. This answer here is negative 2. And pause the video for a second and ask yourself, why would that be true? So I hope what you said is that what the 5 here means is what number times itself 5 times is negative 32. And that number is negative 2, right? So negative 2 times negative 2 is 4. 4 times negative 2 is negative 8. Negative 8 times negative 2 is 16. And 16 times negative 2 is negative 32. In other words, if this index is odd, you can take the whatever root of that value there. You can play with, this is called specifically the radicand. This is also, by the way, in general, is called the argument of the function. So, what about number 15? Can we play with the 4th root of 81? And the answer is yes. You're just answering the question of what number times itself 4 times is 81. And that answer is 3. I always think about 81 in this way. I know 81 is 9 times 9, and I know 9 is 3, 3, 3, 3. And that always helps me to see that 3 times 3 times 3 times 3 is 81. So I don't know if that helps you out, but if I know 9 times 9 is 81, then I know that because 9s can be written as pairs of 3s, that the fourth root has to be of 81 is 3. Okay. So moving right along. Now we have something that's written in a little bit difficult way because we have a bunch of commas here, but we know that this is actually the same thing if I convert this, referring back to scientific notation, 10 to the 6, right? So what does that mean? Well, I said that this is the same thing as saying raised to the 1/6. So again, if I use my exponent rules, then 6 divided by 6 is just going to be 1. So this is 1 times 10. So this is just 10. And there you have it. So because we can pair these up into... Well, how about this? I'm trying to make this sound clear, and I think it was confusing. Think of it this way. This makes perfect sense because if I multiply 10 by itself 6 times, then of course I'm going to get 6 zeros, right? So, easy enough. Moving right along. Square root of negative 100. So hopefully here you realize that this one we cannot do because there is no index, right? So if there's no index, it's even. What I'm really telling you here is that if the index is even, you cannot do the whatever root is of the argument if it's negative. So in 18, there's no work required. This is even. You can't do the fourth root of negative 16 under the reals. 19. So this is kind of an interesting question because one would think that if I did this, I would get the fourth root of 81, which is 3, right? But let me put it this way. So if that is true, then yeah, the answer has to be 3. What I was thinking about is if I wrote it as such and solved, I would get negative 3, right? So now the question begs, is it 3 or is it negative 3? The answer is it is technically both, but because I said what is the principal root, the answer is 3. Okay, so here, I'm going to say this is 3 because I was asking for the principal root. Same sort of argument, right? And and 21, the answer is going to be x plus 2. Because it's the same notion. We take x plus 2 squared and we raise it to the 1/2. It's going to become x plus 2. Now, one other thing here is that if I'm being technical, and you're not going to have to do this for the class, but technically speaking, we would want to put in absolute value bars because I'm asking you for the principal root. But we're not going to get that technical in this course, so don't stress over it. Just wanted to stress that in reality that would be the case. So here's a perfect example of why we want to know that we can write the 6th root as raised to the 1/6, because now we can take these and multiply them together. We get a plus b to the 3/6. 3 times 1/6 is 3/6, which is a plus b to the 1/2, which is the square root of a plus b. All of these are equivalent. Usually the last one is the way that you're going to see it written on an exam. So more of the same. So the square root of y to the 4th, remember the index here is 2, so this is y to the 4th raised to the 1/2. Because I'm raising a power to a power, I can multiply these together and I'll get y squared. Y to the 8th, again the index is 2, so this just means, based upon my work here, this means I'm just simply dividing this by 2, so this is y to the 8 over 2, which is y to the 4th. Okay, so more of the same. When you see it written in this format, remember, we can still separate these, so we can take on the cube root of 27 and the cube root of 80 cubed. And this is my advice. Break it down into 2 separate problems. This is going to become 3 because 3 times 3 is 9, and 9 times 3 is 27. A cubed to the 3rd, remember this is just a cubed raised to the 1/3 power, so that's just going to give me a. So the answer to this is 3a. And remember, if you have any doubt, you can just take 3a times 3a times 3a and see, does that give me 27a cubed? So the nice thing about equality is that whether you start with the left side and you end up with the right, or you start with the right and you end up with the left, they have to match. So you can always easily check your work on these situations. So here, this is the same thing as, again, raising it to the 1/5, which means the 1/5 attacks both of these, so it's just going to be a over b. Because 5 times 1/5 is just 1. 27, again, I'm going to put the numbers on one side, so I'm going to say 81 and 16, and then I'm going to deal with x to the 4th and y to the 8th on the other. So we're going to take the 4th root of this and the 4th root of this, and whatever I do, because it's the negation, I have a negative sign on the outside. So we know the 4th root of 81 is 3, the 16th root, the 4th root of 16 is 2, and if you don't see that as the case, multiply 2 by itself 4 times and you will get 16. Again, I want to stress that practicing your powers will make this a lot easier. You can see I can effortlessly say 16 is 2 and 81 is 3. Maybe not effortlessly, I did stutter a little bit. On the right-hand side, x to the 4th, y to the 8th, we're going to raise this to the 1/4 power, which just means I'm going to multiply 4 by 1/4 and 8 by 1/4, which will give me x, y squared, and then we just bring the rest down. And there's our answer. So the idea here is play with the numbers and then play with the letters, and you won't have too much difficulty. Break it down to the little steps that you already know. Now in 28 is trying to use applications of what we've discussed to solve higher level problems. This question is asking you to recall something called Pythagorean Theorem, which, if you don't recall from your high school days, is a squared plus b squared equals c squared. So all this means, and though I labeled this a and this b, it's okay that this has a on the bottom, right? A and b are just the letters that I wrote initially to denote what each side is. They're calling their specific a, so this a and this a are not necessarily the same thing, in other words. Okay, but all it's saying is that you square these two components and it's going to equal to the longer one. So these two here are called the legs, and if I square them and sum them up, it should equal to the longer one, which is called the hypotenuse. So solving 5 squared, that's 25, plus a squared equals 13 squared is 169. And so if I subtract 25 from both sides, a squared equals to 144. And to get rid of a square, we square root it, and a is going to be 12. Now, some of you may be arguing a should be plus or minus 12, but in the context of the problem, we're talking about length. And because we're talking about length does not have direction. So if length does not have direction, it would have to be positive, not negative. In other words, you don't say that I walked -6 miles. Okay, so 29, 30 are more of the same, so go ahead and pause the video now and try to figure these out on your own. I'm going to assume that you've done so. Now we're going to tackle them together. So we're just going to apply Pythagorean Theorem, which just means I'm going to square each of these. So 12 squared plus x squared equals 15 squared. 12 squared is 144 plus x squared. 15 squared is 225. We're going to subtract 144 from both sides. So x squared is equal to 81. So x has to be square root of 81 is 9. Okay. And number 30, more of the same. This squared plus this squared is this squared. So notice it doesn't matter where I put x. You just say the legs squared. The sum of the legs squared has to equal to the hypotenuse. So this is going to become 144 plus 256 equals x squared. Again, I want to emphasize that the more you study your squares, the easier this will become, and you can effortlessly figure out what the value is going to be. So is that right? 10 carry the 1, 5, 10, carry the 1, 3, 4. This should be a 4 right here. So we get 4 equals x squared. Once more, we take the square root of these. Square root of 400, square root of 4 is 2, square root of 100 is 10, so this should be 20. So x is 20. I want to point something else out about this. This is if you progress in math and take something like trigonometry, the TRI in trigonometry, you can think of it as like triangle. And the 5, 12, 13 is what we call a triplet. And all triplets mean is that if you have them memorized, they come out to be nice numbers. So we have to stress the fact that when we solve these problems, it's not always going to come out as pretty numbers. All of these answers have been pretty. In the real world, you seldomly get that. But if you have these pretty number answers for triangles memorized, your life becomes easier. So if you know 5, 12, 13 is a triplet, if I see 5, if I see 13, then I know the missing link has to be 12 because I already know that this is 5 and this is 13. Another very common triplet is the 3, 4, 5. And I always like that one because it's easy to memorize. It's got 3, 4, and 5. So there are many of these. For the time being, I would tell you, make sure you're aware of the 3, 4, 5, and 5, 12, 13. Something else to note is that on number 29, notice that 12 is 3 times 4, and 15 is 3 times 5. So you can have what's called multiples of a triplet. So if this is 4 and this is 5, notice we said here the triplet is a 3, 4, 5. So that means that this side here has to be 3 times whatever the default triplet was, which is 3. So that means that this would have to be 9. So if you see that every single number for your links is divisible by a number, you may want to do that, and you may, by doing so, by breaking it down, you'll be able to figure out what triplet you're playing with. Okay, so again, for here, notice here, if I divide through by 4 for both of these, I would have ended up getting 3, 4, which means that this one is, sorry, not 3, but 5, because it's 3, 4, 5. Because I'm dividing by 4, this is 5 times 4, which is 20. So if you're comfortable with that, that makes your life easier because you don't have to do all of this work to get to your answer. So it's a fast, efficient way. Again, if you're progressing in math, you're going to play with a lot of triangles as you progress, so you might as well get comfortable with this now. Moving right along, we have domain. Now we know how to play with domain because we know the domain is what can this not be equal to. So we know that if the index is even, we can't take the square root of a negative, so we'll just simply say t minus 2 has to be greater than or equal to 0 because numbers at 0 or more are not negative. So we'll add 2 to both sides and arrive at t is greater than or equal to 2. In 32, let me give you a second to think about what you think the answer is, and hopefully you've thought about it and you're able to tell me. The answer to this one is, in fact, all real numbers. There's no stipulation. And if you didn't think this originally, if you kind of piggybacked off the last problem and try to do the same sort of thing here, or you're thinking of doing that, the reason why that does not work on this one is because my index is odd. And if the index is odd, right, if this value is odd, then it'll work whether it's negative or positive. Because if I had, for example, let's say it's the cube root of negative 8, cube root of negative 8 is negative 2. Because negative 2 times negative 2 times negative 2 is, in fact, negative 8. 33, this is a classic problem. We can say 3 minus 5x is greater than or equal to 0. And we solve, so we subtract 3. And then we divide by negative 5. My one comment would be careful when you divide by negative 5 because you must flip the inequality. Remember, negative 3 over negative 5 is just 3/5. Negative divided by negative is a positive. All right. The next part is asking us to graph. Now, the book is going to talk about graphing in a way I'm not really too big of a fan of, though it does always work, which the book's going to say, just make an X and Y grid and plot points. So I'm going to pick 0, which would give me the square root of 3. Right? If I plug 0 here, I would just get the square root of 3. But I want to get values that work out right. Like I know the square root of 3 is like roughly 1.7, but I would have to use, most of y'all would have to use a calculator to figure that out. So what I'm going to do is I want to pick values that work nice for this. So I'm actually going to pick 2. You might be wondering, well, why, Mr. Anderson? And the reason why I'm going to pick 2 is the square root, if I plug 2 in for x, I'm going to get 3 minus 2, which is 1. The square root of 1 is 1. So I'm actually going to think what would give me 2. The square root of 4 would give me 2, which means this has to be negative 1. And I could plug more and more values. But let me start with these. So I know negative 1 is at 2, and then I know 2 is at 1. So it seems that we have some sort of effect like this going on. Now, I know also that at 3, I would get 0. And I also know that if I plug in a value greater than 3, like 4, I'm going to get a negative value here. So I can't do that. So this seems to me that this is doing something like this. Now, if we look at the graph here, we actually see that that is exactly what's going on here, right? We can see some values that I've plugged in, but this graph gradually shoots up like so. Okay. Looking at 35, we'll do the same thing. We'll make an X and Y chart. I kind of want when it's 0, so we'll say negative 4, because negative 4 plus 4 is 0, and the square root of 0 is 0. Again, we want to pick values that work, so I want to see what gives me 1. That would be negative 3. All I'm saying is negative 3 plus 4 is 1. Square root of 1 is 1. I want 2, which means I want this to become 4, because the square root of 4 is 2. So if that's the case, I want this to be, what did I say? I want it to become 4, so it has to be 0. So if x is 0, 0 plus 4 is 4. Square root of 4 is 2. So that's enough. I know the graph is going to look something like here at negative 4. Then at negative 3 we have 1. And 0 we're going to have 2. So it looks something like that. If we look at the graph, we can see that what I said also is true here, right? One last point that I want to make is that, and I'm not going to go too much into depth because we're not doing too much graphing in this class, but it is in your best interest to realize that what's called the parent function, the square root of x, looks like this. In other words, this is shooting out this way. What this plus 4 actually means is that the graph gets shifted back 4, and over on this one, because it's negative, we actually have to factor out a negative, and we get x minus 3. The negative 3 means you shift to the right 4. The negative on the outside, when you take the square root, changes the direction. So there are certain rules. In future classes, you will learn what these rules are. In the meantime, I'm done with time. See you guys next video.